We're going to finish up this section by taking a look at three equations to where we have trigonometric functions that are going to require some sort of identity to be able to solve. And so we know that we're going to have to use an identity if for some reason we have different angles inside of the trigonometric functions. So notice here that we have a 2x and an x, and we certainly know that we have a double angle formula for this, okay? Or if for some reason we would have two different trigonometric functions. So notice here we have a sine and a cosine, right? So the goal is we always want to try to put the entire function, when possible, into the same trigonometric function. Okay, so whatever identity we use, most of the time, okay, in almost every instance, we're going to have to use the same trigonometric function at some point. So let's take a look at three examples of how to try to employ that sort of technique. So we have the cosine of 2x plus 3 sine x minus 2 equals 0. So clearly this is going to be a problem where you need a trigonometric identity because we have a cosine and a sine. Let's go back to the double angle formulas. Okay, so this is a double angle. And you probably remember that the cosine actually has of 2x has three actual formulas. Okay, so we have cos square minus sine square, 2 cos square minus 1 minus 2 cos square, or sine square, excuse me. And I'm going to suggest that we use this one because it'll get everything in terms of sine, the 1 minus 2 sine square of x. Right, so I'm going to rewrite this by using our double angle formula as 1 minus 2 sine square of x plus 3 sine x minus 2 equals 0. And then I notice that I have a 1 and a negative 2, so I can combine that and make that into a negative 1. I have negative 2 sine square x plus 3 sine x minus 1 equals 0. And then anytime the first term is negative, okay, this is a trick that you can use in algebra all the time. If you have a polynomial function and the first term's negative in an equation, you might just want to multiply everything by negative 1. All right, so that might be a trick that you've seen. And what multiplying by negative 1 on both sides does is it just flips all the signs. Clearly, it doesn't matter on the right-hand side because negative 1 times 0 is 0. And then our equation becomes 2 sine square x minus 3 sine x plus 1 equals 0. Now we can rewrite this as a polynomial sort of equation. And so instead of sine square, we can write that as x. So we might write this as 2x squared minus 3x plus 1 equals 0, right? Just to kind of think of it as a polynomial. And if I wanted to factor this, we could. We could say 2x minus 1, and then x minus 1 equals 0, right? And if you don't trust me, you certainly can just go through and FOIL that out, and you'll see that it does equal 2x squared minus 3x plus 1 when you're done. So I'm going to now write this as the quantity of, instead of x, 2 sine x minus 1. And then instead of x minus 1, I'm going to write that as sine x minus 1 equals 0. Now I can set both of these factors to 0. So 2 sine x minus 1 equals 0. And then sine x minus 1 equals 0. This becomes sine x equals 1/2 by adding 1 and dividing by 2. This becomes sine x equals 1. Right? And then finally, we just look in the unit circle, okay, remembering that sine is the y coordinate, and we look for all locations where the sine is 1/2 or 1, right? And the angles that are going to get us there are going to be pi 6, okay, so that's the first one. And then we know that sine is positive in quadrant 2, so the reference angle would be 5 pi 6. And then the sine is equal to 1 at pi halves, right? And these are going to be our three solutions to that equation, okay? And remember, when we're solving this, we only want to make sure that we're solving it from 0 to 2 pi. A second example, this time we have 4 sine square x plus 4 cos x minus 5 equals 0. Notice that we have two different trigonometric functions. One's a sine, one's a cosine. There's not really any trig functions for cos that can get us the sine nicely, okay? So let's use we could use a Pythagorean identity. We certainly don't want to use like a power reducing formula, though we could, okay? But that would just lead to a double angle anyway. So I'm going to rewrite this as 4 quantity By the Pythagorean identity, this is 1 minus cos square x plus 4 cos x plus 5 equals 0. Now I'm going to distribute the 4. So I get 4 minus cos square x. Oh, this should be a minus 5. Sorry, that was a copy error right here. So that should be a minus 5. Sorry about that. 4 minus 4 cos square x plus 4 cos x minus 5 equals 0. And then if I combine the 4 and the negative 5, that just gives me negative 1. So negative 4 cos square x plus 4 cos x minus 1 equals 0. Notice that we have a negative as the first term, so I'm going to multiply everything by negative 1. Okay, so a trick that we use quite frequently. So now we get 4 cos square x minus 4 cos x plus 1 equals 0. If I think of this in terms of a polynomial equation, replacing cos with an x, I can get 4x squared minus 4x plus 1 equals 0. And that might be a little bit easier to factor. Okay, so I can write that as 2x and 2x, and then minus 1 equals 0, or completely factored because we have the exact same polynomial or binomial next to one another. I could write that as 2x minus 1 squared. And so instead of x, I'm going to replace that with cosine, and I'm going to write this as 2 cosine of x squared minus 1. Oh, sorry, 2 cosine of x minus 1 quantity squared equals 0. Okay. Now I could take the square root of both sides, okay, and that would cancel the square and the square root, so I get 2 cos x minus 1 equals 0. I'm going to add 1 and divide by 2, so cos x is a half. And we know that x is going to be positive in quadrants 1 and 4. Okay, so we have all students take calculus, so we have the all and the cosine in those two quadrants. I believe we're going to end up with pi thirds as well as 5 pi thirds, right? Now remember, I think I told you in one of the videos that if you ever take a square root, you probably should check to make sure that those are both roots, okay, of this, okay? So you want to make sure on the interval that you have two solutions, okay? So I'm going to go all the way back to the beginning of the problem, okay? And I'm just going to graph that, okay? So we have 4 sine square of x. I'm just going to put a 4 out here. I'm going to change this to sine instead of secant. And then what else did we have? I think we had a plus 4 cos minus 5. All right, so we had plus 4 cos minus 5. All right, and that's supposed to be equal to 0. Now, it looks like there are indeed two solutions, because remember, the other equation is we set that equal to 0, okay? And there are two solutions, it seems, right here at 1.047 and right here at 5.236. And of course, those should be pi thirds and 5 pi thirds. All right, so let's just check that out. Okay, so I have pi over 3, that's 1.047. If we go back to the graph, 1.047. And then we're looking for 5.236 at 5 pi thirds. So we have 5.2359, which is 5.236. Okay, so both of these answers are substantiated by the graph, and so these are the two solutions. One final example, and this is a really sneaky one. We have sine of x plus cos of x equals 1. Now, the reason this is sneaky is because there's no trig identity that we can just use on sine and cosine that's going to nicely get us to what we'd like. So the trick with this one is we're going to subtract cosine from both sides. So we get sine of x equals 1 minus cos x. And what I'm going to do is I'm going to square both sides. All right. And so by squaring both sides, I get sine x. This 1 minus cos x, I can write as 1 minus cos x, and then 1 minus cos x. And so that's going to turn into 1 minus 2 cos x plus cos square x. All right, and this should be a sine square of x. All right. Now, I think for us, we'd like everything to be in terms of cosine. All right, just because there's a cosine and a cosine. And so we can use the Pythagorean identity. Excuse me. And so this can be written as 1 minus cos square of x. And we have 1 minus 2 cos of x plus cos square of x. Now I'm going to subtract 1 from both sides, and I'm going to add cos square x to both sides. And so our equation now becomes 0 equals two ways we can write this. We could write this as negative 2 cos x plus 2 cos square of x. Or another way we can write this is if we flip those two terms on the right-hand side around, we could write this as 2 cos square x minus 2 cos x. That's probably how we should write it. Now, I'm going to factor a cosine out of these. In fact, I'm going to factor a 2 cosine out of these. So I get 2 cos of x, and that's going to leave me with cos x minus 1. And then finally, I'm just going to set 2 cos x equal to 0. And then I'm going to set cos x minus 1 equal to 0. Divide by 2 on the first, so cos x equals 0. Add 1, cos x equals 1. And so our four or three or two or three solutions that seem like they're going to work, the cosine, remember, is the x coordinate, and the x coordinate is equal to 0 at pi halves and 3 pi halves, okay, right on the y-axis. The cosine is equal to 1 at 0, okay? Now, once again, we should probably check the answer just to make sure that there's no extraneous roots, because we did square both sides. All right. And anytime you either square root or square both sides, you might be introducing extra roots into the equation inadvertently. Okay. So remember, the equation was sine x plus cos x equals 1. Okay. So we have a sine x plus cos x. All right. And y is equal to 1. All right. Now I want you to notice that right here, we have one of the solutions at x equals 0. Okay. And certainly we got that. And then if we go to our graph, we've got another one here at pi halves. Okay, so that's good. But then we look at the graph, and I want you to notice that the only other solution is 2 pi. Okay, we're missing that 3 pi halves here. That is not part of the solution set. Okay, so this is an extraneous root that's born from squaring both sides. Okay, so that's an extraneous root. And so the only solutions to this are going to be in order in which they appear, 0 and pi halves. All right, so that's finally everything for our trig equations. It's a deep section, all right? It's also an important section, okay? Especially for those of you that are moving on to calculus, you're going to be seeing this quite frequently, okay? So suggestion might be go back, make sure you can do at least one problem from each of the various types, okay? And the four main types, okay, just to kind of recap, we have the really basic types, okay, such as this, okay? So that's a pretty basic type. We had the multiple angle types, okay? So where we have like a 3x on the inside here. So make sure you can do one of those types, right? We had the type where we had the factor, okay? So like, something like this would be okay to practice. These are the ones that you should really spend a lot of time practicing. Maybe something like, this one would probably be good to make sure you can do. And then finally, we had the ones where you had to use an identity, okay? Any of those are good, okay? So those are your four main types. Again, just making sure you know what they are. The first one is basic. Okay? And then you had the multiple angle type. And then you had the quadratic types, or I'm just going to call it higher order. All right. And then finally, you have the ones where you have to use a identity. Right? All right, so that actually takes care of our analytic trig unit. Okay, so we're going to move into another unit after this one, and that's going to be where we start using a little bit of approximations to be able to complete triangles. And we're also going to take a little bit of a look at areas as well as some vector stuff.